well, spoiler alert. Okay, yeah, it looks like it's working now. So, yeah, so I'm going to be talking about if there are independent measurements of the Hubble constant. And specifically, I had the idea to talk about this because I've been researching the Hubble tension, which I'm going to talk about. And this question was something that popped up almost instantly for me. And specifically, the thing I'm researching is the history of the development of distance measurement in astronomy and in modern cosmology, I suppose. And so this question is one that actually is very important to this. So let's take a look. So starting from basically zero knowledge, what is the Hubble constant? So back in 1929, Edwin Hubble, together with his collaborator Milton Humason, they were comparing the redshifts and the distances of extragalactic nebulae, so what we would now call galaxies. And they put together this really nice and iconic graph here, where you can see that extragalactic nebulae that are at greater distance from us are also accelerating away from us, or moving away from us, apparently quicker than things that are closer to us. I say apparently because, of course, at the time it wasn't clear why this relationship was displayed, that things that are further away appear to be moving away faster. Now we would say that this is because of the expansion of the universe. And so instead of the empirical Hubble law, which is just an empirical relation that you get from looking at redshifts and distances of objects in the universe, you could instead give this theoretical definition of the Hubble constant that has to do with the scale, the change in the scale factor of the universe. And then you could use Friedmann equations to understand how the Hubble constant changes over time, depending on the constituents making up the universe, the density of those. So this is sort of the intro to what the Hubble constant is and where it came from, very brief. Okay. But then if you want to talk about how this is actually going to be measured, one of the main methods actually still involves Hubble's original method. So using the empirical Hubble law at the top to look at the redshifts and the distances of various objects and get out a Hubble constant that way. So the first thing that we're going to look at uses this empirical Hubble law. Okay. So this is the cosmic distance ladder method of getting the Hubble constant. So the first step to this is you want to know the distances to things in the universe. You have to start with geometric distances. So the most obvious of these would be parallax, which hopefully we all are familiar with. So you can get the distances to, for example, stars in the Milky Way using parallax. Now this isn't going to be good enough to get you a Hubble constant because obviously the stars that are in the Milky Way aren't moving away from us with the expansion of the universe. That would be pretty interesting, but they're not. So if you tried to get the Hubble constant this way, you wouldn't really get anything. So you need to move further out to things that are moving away from us with the expansion of the universe. All right, so you have these geometric distances from parallax of things in the Milky Way. Let's take a step out. Instead, we can look at Cepheid variable stars. Cepheid variable stars are nice because there's a relationship between their period and their luminosity, discovered by Henrietta Leavitt-Swan. And basically for two Cepheid variables, if they have the same period, then you know that they also have the same intrinsic luminosity. And so if you have two of them, they have the same period, they should have the same intrinsic luminosity. If instead one is fainter than the other, you know that that one is further away. So this allows you to get relative distances between Cepheids. You know the fainter ones are further away, but you need to be able to get absolute distances. And so that's where that geometry comes back in. If you can get the parallax distances to some of these Cepheids, you can get the absolute calibration of the Cepheid period luminosity relationship. Sadly, Cepheids are also not far enough out where you can get the Hubble constant, so you're going to have to go to something else. The usual case, you'd go to type 1a supernovae. The reason you go to those is because they're all believed to have the same intrinsic brightness, kind of. There's some, little problems there, but roughly they all have the same intrinsic brightness. So it's the same scenario. If one is fainter, you know it's further away. That gives you these relative distances. And you can use your absolute calibration of the Cepheids from the parallax to get to the distances of these type 1a supernovae. So that's why it's called the cosmic distance ladder. You're climbing up through all these different steps to get at the distances of things that are further away. I won't bother to talk about the redshifts because there's no controversy there. It's not very interesting. But the Schutz team, led by Adam Rees, they build this type of distance ladder from geometry to Cepheids to Type 1a supernovae. And they've been doing that for almost 20 years now. And their most recent results, I believe last year, is that the Hubble constant is 73.3 plus or minus 1 kilometers per second per megaparsec. Okay. So this is one method using the empirical Hubble law to get at the Hubble constant. The other major method is using this observations of the CMB. So if you want to talk about the best observations of the CMB, you would look to the Planck Space Telescope. So the CMB is here. We've talked about it a few times today at this point, but it's mostly homogeneous, but there are these anisotropies throughout it. And by looking at those, you can learn a lot about the physics at the period of recombination. So essentially, after the Big Bang, things start to cool down, neutral hydrogen is able to form, and photons are released, and this is the period of recombination. Now, because of the initial overdensities in this plasma, you get these acoustic oscillations that are being set up as these initial overdensities gravitationally collapse and then expand as they heat up through radiation driving, and then recollapse. You get these acoustic waves. Then when recombination happens, photons that are released in one of these sort of overdensities have to climb out, and so they'll be redshifted relative to the rest. Now, why does any of that matter to the Hubble constant? Well, if you look at this equation up here, which is a little off kilter, but so one thing that you could theoretically calculate if you knew something about the physics at recombination, like the speed of sound of this acoustic wave, is the sound horizon scale. So this is the distance that one of these acoustic waves could have traveled before recombination. And then something you could hopefully measure with the Planck Space Telescope would be the angular scale of that feature on the sky. So if you could observe that feature somehow, then you'd be able to get the angular scale, how large it appears on the sky. And thankfully, this angular scale is something that can be observed from the first peak of the temperature power spectrum, because you'll see correlations in the anisotropies because of the redshifting from this era of recombination. And then, if you take the ratio of these two things, the angular diameter distance is the expansion history since recombination. So if you can constrain all of the other things that would go into this, you can get the Hubble constant sort of out. Okay. So it's a much more, let's say, model-dependent measurement. Some of the people who do the cosmic distance ladder wouldn't want to say that it's a measurement at all, that it's just a prediction of lambda CDM that you get from observing the CMB. And they would kind of be put off to the idea that this is a measurement of the Hubble constant at all. I'll just use measurement in a very neutral way. But when they do this measurement, the most recent Planck data release in 2018 gave a value of the Hubble constant of 67.4 plus or minus half a kilometer per second per megaparsec. Okay. So hopefully now everyone is, in shock on the edge of their seats, because this value is not 73 plus or minus 1. And so there is about a 5 sigma tension between the cosmic distance ladder that I was talking about earlier and the Hubble constant you get out of these observations of the CMB. So to give a little bit of a context, so you can look at how this has kind of emerged over time. So we were talking earlier about whether or not particular measurements sort of hold up under increasing precision, and it's actually the increasing precision that has driven at least some of the divergence here. So if you look at the red, I don't know what you'd call this, portion of the graph, we're starting in about 2001 the Hubble Space Telescope Key project. So one of the main projects of HST was to measure the Hubble constant using geometry to a bunch of things, including Cepheids, and then type 1a supernovae. And at the time, yet the error bar looks big now in comparison, but at the time, this 10% measurement was incredible. It was a huge leap over what had come before. And WMAP, so the Wilkinson Microwave Anisotropy Probe, they released their first measurements a couple years after that. And you can see that for a while, everything was really good. I kind of have a suspicion that if you're someone who measures the Hubble constant, this was the only good time to be alive, in a certain sense. Because the rest of the history, unless you like arguing, then this was maybe the worst time to be alive because things looked really good. So if you read papers from that time, it's sadly incredibly optimistic, where people are saying things like, all of the old arguments are over. We not only have a nice concordance cosmology, but it agrees perfectly with astrophysical measurements. And yeah, you read that now and have to shake your head a little bit. But okay, so things stayed all right for a while. And then you can see that they start to diverge. So everything on the top is a distance ladder measurement, primarily the geometry Cepheid supernova ladder that I was talking about. And then, ignore the BAOs for a second, but the bottom is all observations of the CMB, aside from that. So this is kind of the state of the Hubble tension right now. It's this particular divergence between these two measurements. That's how I think it's the easiest way to kind of think about it for now. Okay. So before I move on to the next portion, maybe it would be good to make sure that people are understanding at least roughly how the two measurements are done and what the tension here is supposed to be, just if there are any quick questions there. Okay, it looks like that's a no. That's good, that means I explained it perfectly. All right, so what are the potential solutions? I mean, as you can see from this, this has been a problem for over a decade. I think the first paper to start really pointing out that there was an issue was actually as early as around 2006. The Shoes team was pointing out that there might be a little bit of a problem here. So this has been going on for a long time. So what are some of the solutions people have brought up? Well, you could say that there's a problem with the Planck data or the analysis of that data. I don't mean the cosmological model, I just mean, the way the data is being actually reduced and analyzed. This isn't really something that people consider to be a live possibility. It's not something people really bring up in the context of solving the Hubble tension. I just mentioned it because I suppose it's, theoretically it's possible. What more people kind of pick at is that there could be a systematic error in the cosmic distance ladder. So something that's just skewing the measurement of the Hubble constant a bit too high. And so as an example of the type of thing that people would talk about here, there were worries with the Hubble Space Telescope that the resolution was such that when you're observing the Cepheids, they're kind of on this field of other stars. And so if you're trying to get this good photometry of the Cepheid throughout its period, the fact that it's crowded together with other stars is maybe going to make you worry that you're measuring them as their brightness is a little bit off. And so this was called overcrowding. And for all of the sort of modern uses of Cepheids as a distance indicator, this was something that people really have worried about for a long time, this overcrowding issue. And it came to be something people could go to with the Hubble tension and say, well, I'm reserving judgment because, potentially this is overcrowding. Now, as of very, very recently, because of JWST, people think that that's not really an issue anymore because the greater resolution allowed the Cepheids to be separated out from the other stars, and it seems that this wasn't contributing anything to the Hubble constant measurement. So all of these sources of systematic error are kind of being, rejected sort of one after the other. And of course, people make more suggestions of potential sources of error, but none of them have quite worked out just yet. Another way people go is to theorize about new physics. This is the go-to phrase for this. So new physics could either describe these early time solutions, which alter the physics before or at recombination, so doing something to change the scale of the sound horizon. Or it could be something, late time solution, that does something to modify the expansion history. And if you look up new physics solutions, I think I've had some fun with some of the people here talking about all of the possibilities here. I mean, there are hundreds that have been suggested. I included some of the ones that people maybe take a little more seriously here. So early dark energy, interacting dark energy, where it's coupled to dark matter. Modified gravity, but only specific types of, not just like any modified gravity will do much of anything. So some of these are, you know, if you're seeing the potential for modified gravity, that's something that's pretty significant paradigm shift here. You can maybe see why people are getting a little bit worried about the Hubble tension, focusing more attention on it, because people are bringing up these real possibilities of theory change in response to it. Okay. So this is why I had to plug in my laptop. I wanted to be able to show everyone this slide. Let's see. Oh, good, it did work. All right. So before, when I was saying that the Hubble tension is an issue between the SHOES distance ladder and the CMB observations by Planck, that's a little bit of a lie, maybe, but that is how it's usually described. So, of course, there are many, many, many ways to measure the Hubble constant. And so this really nice graph from a paper by Di Valentino lays out a lot of them. I mean, obviously, it's not telling you anything about the method, but this can give you a sense for kind of the number and the variety of measurements. So you can see the sort of the pinkish, I guess, outline here is the Planck H0, and the blue is the SHOES. So you can see how things line up. And you can see from the way she's put this together, people will usually call the things on the top like early measurements of the Hubble constant, because these are things that have to do with either recombination or they're more cosmological measurements. I think all of these have to do with physics at recombination, actually. And then the bottom are the late measurements that have to do with measuring the Hubble constant at much lower redshifts. Also, you know, maybe you could read into something about the fact that these are also being labeled indirect and direct. Again, this is kind of this idea people have that there's something a little suspicious about the model independence and dependence of the two classes of measurements here. All right, so, I mean, to be clear, plenty of these are types of distance ladders. And so this is the sort of thing that got me thinking about this issue of independence. Yeah, sorry.
Can I ask what?
Yes.
So in the other graph, there was the nice period where everybody thinks they're in agreement.
Mm-hmm.
I can't quite see it in this picture.
Oh, well, this is not over time for the most part. I mean, there are, you know, some older and some newer measurements in here, but this doesn't have the early W map, I don't think, unless
okay.
yeah.
I see. So there was some, okay, so there was some CMB without Planck that were kind of more in alignment with the Cepheid.
Yes, so like Atacama, yeah, South Pole Telescope observations, yeah. So yes, this is not over time. Yeah, that would be strange. Okay, so yeah, so this is from, I think, 2 years ago. So, I mean, there are some additional things, and of course there were measurements that were left off of this, but this kind of gives you a sense of the variety here. And this type of really long graph of, or chart with all of these options, it's used both in an argumentative way and a sort of rhetorical way. I don't know if that's the right way to put that. Showing this type of image is something that's used kind of to make an argument when people are talking about the Hubble tension. So for example, the people who were doing observations of these direct H0s, so the people in the bottom half, sometimes they'll say, you know, how can you think that there's a systematic error in our measurements? Look at the agreement between all of these different measurements kind of clustering together around this value. And likewise, you know, for the people on the top. And sometimes I think it's the like actual length of this type of image that sort of makes the argument. Okay. So all right, so this is a similar thing, but in a more easy to look at format, so we'll stick with this one from now on. So something that kind of immediately jumped out to me as being interesting when I was looking into these distance measurements is that, to some extent, all of these are described as being independent. But the way in which they're supposed to be independent isn't always clear and doesn't seem to always mean the same thing. So just as one sort of small example that I won't go into the details of too much, if you look at the one that's labeled MCP, this is the Mega Maser Cosmology project. So they are able to get these geometrical distances to water megamasers throughout the universe by looking at the orbit of these water masers around the nucleus of the galaxy that they're in. And the very first maser in this chain, it's called NGC 4258. Well, that's the galaxy that the maser's in. And NGC 4258 is used by SHOES and the CCHP, the Carnegie Chicago Hubble program, as an anchor for their distance ladder. So I had said you need these geometric measures to get out to your Cepheids, to get out to your Type 1a supernovae. Parallax isn't the only one. These masers are another one. And this first maser that the MCP looked at is one that's used by other distance ladders. But again, the interesting thing is that with all of these, there is an independence claim that's being made, sometimes in the abstract of the paper, sometimes more rigorously throughout it, about how these are independent measurements. And so that type of small thing was what kind of, caught my attention to look a little bit more into what was going on here. Okay. So how are people using the term independent here? The first, as I've already said, is supposed to be a claim about the CMB versus the cosmic distance ladder. So are these early time versus late time measurements. And again, I already kind of went through it, so I won't belabor the point too much. But what's going on here is this idea of model dependence versus model independence. And specifically the idea that the distance ladder measurements are independent tests of cosmology. So I wanted to mention this exact quote. So if you look back at the start of the SHOES project to measure the Hubble constant, they explicitly say that they saw an emerging tension between supernova measurements and more cosmological early time measurements. And they said they were forming their group because they thought that something interesting would be learned from an independent determination of H0 of comparable precision, and that this would provide a test of lambda CDM. Okay, so, and it wasn't actually just the astronomers constructing distance ladders who said this type of thing. If you read the early WMAP papers, they say the same thing. They say, we're doing something totally model dependent. We need empirical observations to test our cosmology. Now, of course, at the time, they thought that these empirical observations were agreeing with them, so they thought they passed the test. Now it's not so clear that that's the case, so people don't talk about it as much. The next way that you might be thinking of independence is the use of consilience or robustness arguments. So actually, the previous presentation was perfect because we saw a type of consilience argument in action, so I don't have to explain too much what it is. But it's just this idea that if you have independent lines of evidence for something, in this case, a particular measurement, that provides this really strong evidence that the measurement must be accurate. Because wouldn't it be just an odd cosmic coincidence if there was this jumping together of all of these observations, to use a very traditional phrase when you're talking about this type of thing. There's this jumping together of all of these different observations towards the same conclusion. What an odd coincidence if they all pointed us in the wrong way. Now, of course, what really matters here then is the independence. If you have a bunch of totally dependent observations that all point to the same thing, maybe you don't feel as strongly that that's giving you anything very epistemically interesting. I mean, yeah, they're all dependent measurements pointing in the same way. It's not quite as interesting. So to make this type of argument, you actually need to analyze the independence of the particular observations. And then last, sometimes it's being used to talk about sort of security or freedom from particular systematic errors. So I have started calling this quasi-independence, or you could just think of it as independence with respect to some particular source of error. So to give a really extreme and maybe too simplified example, if you were worried that in a particular observation, the team who had performed the observation had just fudged a bunch of the numbers, and then another team replicated the exact same measurement, and they got the same results. Of course, they're not fully independent if they're using the same data, the same method, the same everything. They're only independent with respect to the two teams performing the measurement. But of course, that might be exactly what you're interested in. You want to know that that source of error you were worried about, which is the team fudging the numbers, isn't what's actually causing the result. So all of these are things people might be talking about when they're talking about the independence of the measurements in the long chart that I showed you. So then, once I kind of thought some of this through, the question is, how do you actually go about assessing if two things are independent? And the first of these is, I think, what most people would think of, this idea of two things being, a failure of independence would be if two things are sort of directly entangled in some way. So this would be if a measurement uses the results or the methods of another measurement, or if you're just explicitly pegging one result to another result so that they're actually intercalibrated. I kind of was thinking of this as being a failure of independence on paper. If you had someone detail the way they're making the measurement and they wrote out all of their modeling assumptions and methods, you could compare that to someone else's paper of their measurement and kind of see these clear shared aspects that would show you that they're not independent. But then the thing that is maybe a little bit more difficult to assess is a sort of historical entanglement. So when you think about these measurement methodologies, they're being developed over, in the case of some of them, over 100 years in tandem with other measurements. You have to make modeling choices without necessarily knowing which choices are the right choices to make in terms of getting you to an accurate value. And so as these measurements are being developed of distance, something that is really prized as an indicator that you have a good methodology, that you have a good distance indicator, is the coherence of a particular measurement with others. So obviously if everyone else is getting 70 and you develop this new method that gets 20, people might not take it very seriously, right? And so if you looked on paper, you wouldn't think all of these values getting 70 are somehow dependent on each other. But the agreement between them is going to be a little bit artificial if the reason other indicators or methods were sort of kicked out was just because they failed to have this coherence with others. Okay, so that was at a high level. We can look at some specific examples if we have hopefully enough time. So the first example is going to be addressing the first use of independence that I brought up, are the CMB and the cosmic distance ladder fully independent measurements in terms of one being cosmology independent and one being cosmology dependent. So again, we're going to be looking at Planck and shoes here. And the answer to this question is no, they are not independent. And it's not the case that cosmic distance ladder measurements are cosmology independent. Why? Because earlier when I told you that people are using the empirical Hubble law to measure the Hubble constant, I was sort of lying. I think you know that when you look at great distances in astronomy, you're also looking back into the past. So in order to get a present-day Hubble constant out of whatever the Hubble parameter was at that redshift, you have to know something about the evolution of the universe in between those 2 points. So this is a cosmology-dependent measurement. Now, thankfully, other people have also thought of this, not just me. So this team led by Davan, they actually went and attempted to model the effect on cosmic distance ladder measurements of changes in the assumed cosmology. So changing the way the universe, expands or other things in between the hz that you're measuring at and the h naught that you want to get to. So I really love this paper because they actually sort of saw that this was an issue and tried to assume a variety of different cosmologies to see what would happen. And thankfully, it seems like, at least at the distances people are measuring h naught, things aren't super sensitive to the cosmology that you're using, but of course that's for a very limited range of possible cosmologies that they were exploring. For example, they only looked at flat models. They looked at a very constrained set. And they also only looked at the impact that these changes would have on the cosmic distance ladder. If it's the case that cosmology is going into both the distance ladder and the Planck measurements, then, and this is a very important point, any potential solution that wants to fiddle around with cosmology in order to change one of the values of the Hubble constant needs to be sensitive to how these changes will impact both values. And this is not what's typically done. Usually people will say, okay, this suggestion is going to change the expansion history after recombination. It's a late-time solution. Here's how that changes the Planck value. But really, you should be ensuring that it's not also changing a Schu's distance ladder as well. So this was kind of an attempt to get at some of these issues, but it's kind of a first step. But still, I really love the paper, so. Okay. So then you have these early universe measurements. So it's not just Planck looking at the CMB. And you might wonder, are there independent measurements of h naught from the early universe? Now, what people will usually point to as being this independent measurement is the baryonic acoustic oscillations. So, like the Sloan Digital Sky Survey has done some of this work. So, what you want to look for here is that at recombination, there was this sort of dragging of matter along with the photons until the end of the drag era. And so this creates a characteristic scale that you could potentially view if you look at matter. So if you look at these galaxy surveys, this is obviously a crazy exaggeration in this image. Galaxies don't cluster in these nice rings. That would be really good. But hopefully you could find these sorts of correlations that would be characteristic of this drag radius. And so if you could measure, again, the angle of that on the sky from these sky surveys, then potentially you could get another value of the Hubble constant, very similar to how you get it from the Planck CMB. Now, while this is, an important additional constraint, it's not the case that it's fully independent. Obviously, this is assuming a lot about the fact that, this even results from recombination era physics. You have to know something about the physical size of the drag horizon, just like you had to with the sound horizon. And while there are some ways to kind of fiddle around with this and sort of change what it is you're taking from Planck, it could be a prior on matter density, or it could be this modeling of the recombination era physics. It's still very dependent on the assumed cosmology. Yeah, that's all I'll say about that for now. Okay. And then there's all of these late universe, there's all of these late universe measurements that I've been talking about. Is there independence here from one another, even if not relative to assumed cosmology? And the answer here again is no. So I mentioned that a lot of these have to use the same maser as a first run, or they have to use the same parallax measurements coming from Gaia, the Gaia telescope. There's detached eclipsing binaries, which are in the LMC, so you could go that route. But these are the only first run geometric distances that have to be used really by any distance ladder. So any distance ladder is going to have, if there are systematics in these rungs, in this first rung, it's shared by all of them. And then to get into a bit of the historical entanglement that I was talking about, these distance sliders use objects that have been refined as distance indicators for the past 100 years. And like I already was mentioning, they were then subject to all of this coherence testing, intercalibration, sanity testing, this type of thing. And if you look back to like the 70s, there were a lot of distance indicators being used to measure cosmic distance and get at the Hubble constant that are not being used anymore. And of course, some of them aren't being used because they're not good. They don't indicate distance very well. But for some of them, you could make an argument that they stopped being used because they didn't cohere well with the other indicators that get you values in the range of 70. And the people who were very sensitive to this issue were Alan Sandage and Gustav Taman. They were very critical of this process of selecting distance indicators that all sort of cohered with one another. And in a paper that really cracked me up, they called this the lemming problem of follow the leader, where people are selecting their method and their indicators based on what will get you agreement with other ones. All right, so I think I'm about out of time, so I'm just going to briefly go through then what I saw as the recommendations here. And I'll cut to the chase and point out that I think that these are something that could apply to a lot of different people. So first, instead of just using this blanket statement about the independence of a particular measurement, I think people should start getting more clear on how something is supposed to be independent and from what, and what this independence is supposed to be getting us. Is this a consilience argument where you think the independence is getting us this argument for the agreement of a bunch of lines of evidence? Are you testing for particular systematics, and if so, which ones? This is something that I think falls a lot on the astronomers. Second, when developing new physics, you need to make sure that if these aren't fully independent observations, that when you're fiddling around with one, you aren't accidentally breaking something in another. So if these are dependent, then potentially changes in one could be changes in another. And this is something that you can kind of see playing out occasionally. So this one's kind of on the cosmologist to maybe reach out to the astronomers and make sure what they're doing works. And then finally, for the philosopher and historian, looking at not just this direct dependence that I think people are used to thinking about, but this historical process of refining measurement and creating coherence that you could potentially take to undermine some of the previous independence arguments. And really getting clear on how, over time, different parts of measurements were dependent on each other, if they were, and what all of this is supposed to mean. Okay. And I put in tiny letters at the bottom, maybe at least in terms of Hubble constant measurements, stop thinking in terms of independence altogether, and just start doing what I said in the first one there. But maybe that's too bossy, I don't know. Okay, so that's what I wanted to say.
So, thank you. It's hard to look at you because the microphone is over here.
Oh.
Well, look. So thanks, that was really terrific, like beautiful. To learn about this tension problem, and then the analysis I really like a lot, so thank you. I guess I'm going to try and focus on sort of some of the philosophical issues, since that's my thing. And so maybe one thing that's sort of very much in support of what you're saying, and I think it's just such a rich arena for exploring the notion of independence. So one that I think, I don't know, just an image or a piece of philosophy of science that might be helpful for sort of carrying on thinking what you're talking about here. But another point where I'm going to, I guess, question a little bit more. So the first one is, there's a lot of philosophy of science which you can sort of think of coming here, like large literatures on auxiliary hypotheses. But one thing I really like is, and I use a lot in my teaching, is this image from Bruno Latour of black boxing. So, there's a lot going on in his work, but that image in particular, the stories and his sort of focus on how, in the first place, he has examples of literal machines, computers, and the controversies and debates and conversations and arguments that go into making the machine the way it finally sort of is, but then you put it in a box and you don't think about what's inside it anymore, and then metaphorically the same thing happens for hypotheses. So I take it, maybe that's what sort of Sandage and Tammond sort of have in mind. This may be a case where you have to actually go back and you have to know what's in the black box, and I think, part of what Latour is talking about is, it's actually really important for the progress of science that in general we don't look in the black boxes, and we make new black boxes with the ones we've got. And so it is very, it does cause tension when you have to actually, but you're in a position where you may have to do that. It's not a natural kind of position, I think. So I'll ask both the questions, and then if that's okay, and then let you go there. So if that is a question, what do you think about that sort of image here, will be the first question. So the other one was, I don't know, can you get this?
Yeah, I think it just went to sleep.
Yeah, so there was a slide where you sort of had 3 senses of independence. And the question was, yes, about whether there's really 3 or just 2 here in some sense. So let me ask that. So the model independence, yeah, that's fair enough. Let's put that to one side. But these 2, I'm not quite clear. All right, so we think about the consilience arguments. So this came up in the, as you said, in the dark matter, and you mentioned Perrin. That seems to me, in that case, slightly different from here, because I think the thought is there. We don't know whether there's dark matter, we don't know whether there's atoms, but the fact that all these measurements on the assumption give the same number suggests that they really do exist. Whereas here, we do think there is a Hubble constant, and the question is, what is its value? So I don't see that the consilience argument is quite working in the same way. So what I do see is the sort of worry that whether you have consilience or not might be that, well, is there a systematic error? There is some number, but we're measuring it in different ways, but they all make the same assumption. So they're all putting us off 10% in a particular direction. But that then sort of sounds like the worry in the third one. So really the worry here is what you want for consilience. Yeah, the sort of worry here is the same one about sort of systematic error. Or is there something else that will help distinguish these 2? Does that make sense?
I think I see.
Okay, but thanks again. I think it's really interesting. It's great.
Thank you. Yeah, I'll start with that one, I suppose. So yeah, I guess in my mind, the second one is like the extreme case of the third one. Okay. So I guess it would seem to me like a lot of times what you're getting at with this consilience, like a real consilience argument, is that the 2 measurements are truly so independent that they don't share any potential sources of systematic error, and so that's what's supposed to be giving you this kind of security, right? So it's like a very extreme version of the third one. But you can have still independence according to only a subset of systematic errors, which is how a lot of people are just using the term. They're just saying it's independent, but what they mean is it's independent with respect to a particular thing that they might not be specifying. So whether or not it's different for something that's a measurement, I don't know. I don't think so, because I think that when you're talking about the measurement of the Hubble constant, you're in this sort of, what is it, the experimenter's regress. Now we're just going to talk about STS concepts. You're like black boxing. So you don't necessarily know, how do you know your methodology is good? Well, if it gets you the right answer, but you don't know what the right answer is, so you have no way of knowing if your methodology is good, right? And so I think the consilience is being used to say something about how, yeah, I might not be convinced of this methodology, but the fact that there's all of these independent ones that are getting you to the same measurement, it's both giving you trust in that measurement and trust in the methodologies. It's kind of supposed to work both ways, I think. I don't know if that was answering what you were saying.
Yeah, I think that's I think then it sounds like that's obviously a bit more sophisticated than the picture I had, but I think it's basically in the same line, that the second 2 aren't as aren't as different. I mean, they're more like each other than they are the first one. But
I think, yeah.
and you said one is sort of an extreme case, the other. So, and I definitely like, this idea of being very careful about independence, not just being one thing, but having to be very clear about with respect to all the many different things. I think this is.
Yeah, this is less supposed to be the framework you would give if you were developing a philosophical account of what independence is and all of its senses, and more a description of the ways people are using it.
Yeah.
So yeah, and the ways people are using it are maybe not the same framework you would lay out. As far as the black boxing, I think that that's a really interesting way of thinking about it that I hadn't considered, because it does seem like the cases where you then want to or would have to open the black box are these types of cases of controversy, where suddenly the details are important and you can't just kind of assume them, in this background sort of black box way, when you have the input going in and then the black box shooting out the answer. If it's not shooting out an answer anymore, if the answers are kind of crazy, that's like the reason that you have to open it up and look around. So I think that's right, is that this process of kind of putting aside the history, it's totally common. It's not a suspicious thing or a unique thing that's happening in this case. But I think because of the controversy, that's why then people are kind of going in and looking at this.
Yeah, I think in most cases,
It's a good thing. You have to do it.
Yeah.
Otherwise you don't get anywhere.
Yeah.
Nick, do you have more?
No, I'm good.
But so then I wanted to pass the microphone to Chris Link, who had the follow-up question, I believe.
So I have two questions. One is, in particle physics, it's a common practice to do a blind analysis where you carefully do all your systematic analysis before you determine the value. And I thought that had been adopted recently by the Rees group and some of these other teams. So I'm curious whether you think that mitigates some of the lemmings effect that Sandage was worried about.
Yeah, okay. That's a really good question, because this is something I've been thinking about a lot. I actually think that this methodological change is incredibly interesting, that people are doing this type of blind analysis now. I think that there are potentially a few issues. So, I'm sorry, I was thinking about like how much detail I wanted to give about this, but for example, one group that is doing this is the Holy Cow team, who's looking at quasar lensing. And they do this type of blind analysis, but the kind of quibble that I have, or serious objection that I have, is that in order to validate that their procedure was working at all, they analyzed their first lens not blinded. They unblinded it, got checked to see that the Hubble constant they got was the sanity check, make sure it's around 70, and then they applied it to all the other lenses, blind. But then I think there's a serious issue there of, if that first one, when they had unblinded it, if the value had been something kind of unexpected, there are so many choices that go into modeling the mass of the lens and all these different things that it's easy to kind of go back in and again tinker. And I don't mean to imply it's like nefarious, but there's just a lot of choices that you can make along the way. And so then you can kind of question, well, to what extent is this really blind when, again, the procedure is being validated against an initial Hubble constant output on the first lens. So that's the case I'm familiar with this blinding. I think in the Shoes team, the way that they kind of do it, I could be wrong, but I think it's like sort of breaking down different pieces of the analysis to different people so that there's sort of no one individual who can kind of say, well, I'm going to choose this extinction correction and this way of modeling the Cepheid, period luminosity relationship to kind of get us where we want to go. That type of distribution, I think, can potentially work to ease some of these problems. But again, a lot of these methods that they are breaking up among different people, they're methods that have been developed, I mean, like I said, for the past 100 years. They're already you already kind of know how to do it based on your experience doing this analysis of other data sets and for other Cepheids. So again, it's this question of what does the blinding really mean? What is it actually doing? And I think to determine how significant it is, you actually have to dig into the details of what they mean by blinding and like what's actually going on in an individual case for each group. Yeah.
I have a second question.
Yeah.
So This is just, I think this is a point that Wendy Friedman made at one point, but so if you look at like the TRGB analysis versus the Cepheids, you can in principle just ask, look at the galaxies that have objects of both types and look at their distance estimates. And I believe their distance estimates disagree even for some, and that might also be true for some of the ones they're using for calibration.
Yeah.
Right, and so if that's the case, it looks like you already have a discrepancy that then would be propagating through the analysis. And I wonder if the more recent reanalysis by like, because I know the Reese's team is now doing TRGBs.
Cats.
Yeah. So have they resolved those discrepancies? Or I mean,
yeah. So okay, that's another great question. So in terms of these individual distance disagreements, I don't know. I feel like I need to dig in a little bit more to some of the numbers here because the actual overlap of galaxies that host Cepheids and are good TRGB measurements, it's not very high. Yeah. So if you're talking about a much larger sample that's being used, any potential small quibbles could be washed out in a larger sample. So I don't know how much you should lean on these like individual distance discrepancies. To be honest, I'm not quite sure. As for the reanalysis by the Shoes team, that came out this year, I think, a little bit earlier this year. So for people who don't know, there's another distance ladder, the Chicago Carnegie Hubble program put together. I mean, they have plans to do something kind of beyond this, but right now, the distance ladder they have goes from geometry to tip of the red giant branch to type 1a supernovae. They want to try to replace the other rungs, which we'll see how it goes, but for now they've sort of replaced these Cepheids with tip of the red giant branch. The tip of the red giant branch is just a feature on a color magnitude diagram where you have stars that evolve off of the red giant branch, and you can sort of find this peak, calibrate the brightness of this peak, and then use that as a distance indicator. And okay, so the Carnegie Chicago Hubble program did this, and they got a Hubble constant of around like 69 or 70. A lot of people were really intrigued by this because that's obviously about halfway between Planck and Shoes. Now, there are some real, remaining questions with TRGB. The Cepheids are incredibly well studied, and I think the systematics are well understood. TRGB, it's not like it's a new measurement. I mean, people have been using it for a long time, but it was only recently that observations were good enough to use it to get a more precise Hubble constant, a competitive one with Shoes. And the Shoes team redid this analysis using machine learning. I'm not a computer person, so I mean, it's like artificial intelligence or something, I'm not sure. But basically, when you're using tip of the red giant branch, there's a lot that goes into selecting the fields, so the observations at particular points in the galaxy, and then sort of selecting the region of the color magnitude diagram with the red giants, cutting off the data, processing the data, detecting the edge. That is, for some people looking at it, they think there's just a lot of room for subjective kind of, you can sort of choose to cut the data off a little bit further. You can sort of choose to use one edge detection algorithm over another based on the results it gets you. And there's a lot of potentially more individual choices that can go into it, right, that are a little bit less well constrained. And so the Shoes team redid this using this machine learning where they trained it on some sample data for detecting TRGB, so then in every other galaxy where they were observing it was in a consistent way done by this algorithm. And they get a Hubble constant, the CATS team, of like 73. So it's like the Shoes value. So, I mean, maybe there's something odd about the fact that the same people keep getting the same values, I don't know, but so that's the redone analysis. I, to be honest, don't understand enough about the way they trained this algorithm to do it to say one way or the other, but I mean, I do think there is something kind of interesting about this move to get rid of some of these more subjective choices in the analysis and move towards, a more algorithmic determination, a more consistent determination. So.
It's good. I have questions from Adam, Sean, and Katie, and I remind the others that if you have a question, please raise your hands with a plain open hand, and if you have a follow-up, just use a finger to let me know. So Adam.
Well, you can skip me. Chris asked better forms of both of my questions. They've both been answered in more detail than they would have been if I asked.
So Sean.
Oh, yeah, thanks for the talk. It's super interesting. I like it as like a case study for theory-related misobservation. But I was curious about the sociological mechanisms here, and because you called it historical entanglement. So one field where this happens a lot is election polling, and they call it herding. And I think one of the mechanisms for that is that, like, because you have an election that will tell you who's ultimately right. If you have an outlier, if you're an outlier and you wind up being wrong, then you take a big reputational hit from that. So it's better if you're wrong to be wrong with like a group, with a herd, and then you can kind of shelter behind them and say, well, okay, we were wrong, but so were all these other people. And so, but like it feels like there's that mechanism, or at least the same kind of mechanisms are not at play here, because if you are in one herd and then you found the answer that will belong to the other herd, then okay, sure, people in your herd would not be happy with you maybe, but everybody else would be. And and then you could be like the beginning of a new way of thinking that, okay, maybe your herd is wrong. So there could be some advantage to having that rather than to hide your own result or not publish it or whatever, or be skeptical of it. So yeah, I don't know. I guess it's not. I'm trying to find a question. I mean, what do you think about these? Is this really incentivized the right way, or am I thinking about it the wrong way, maybe?
No, I see what you're saying. I mean, I think it's like I think at every philosophy conference you have the right to say what you think and then turn it into a question by just saying, what do you think about this? It's allowable, it's fine. Yeah, so are the incentives the same? Look, I don't think that anybody is like, I don't know how to put it, like intentionally getting a 67 Hubble constant out of an astrophysical measurement and then saying like, I'm never going to publish this, I'm hiding this under the bed or something. I really don't think that's what's happening, but I think that there is a genuine issue here of you don't know which methods are accurate distance determination methods. And a big way that people assess this is coherence. And so it's less that, people are intentionally hiding it, and it's more an issue of comparing your value to others as a sanity check, this type of thing. And I also think, people will publish slightly lower values, but a lot of times they don't get any traction because people will say, well, why is this different from all the other ones say whatever, to be clear, I mean, I sound right now like I'm being very critical of cosmic distance ladder. If you made me place my bets, I'd say the Hubble constant 73, so don't get me wrong, don't get it the wrong way. But I do think there are still incentives if you're developing a new distance ladder to have a value that is coherent with the other ones. I guess as a sociological point, something else that could be said is that, the PI of the SHOES team, Adam Rees, has the Nobel Prize. So maybe there's a sociological element of kind of trust going on here. Not in a bad way, but in a way that at least, it gets people kind of on board with this higher value that maybe otherwise people would be more skeptical of and go along with the cosmological side. So there's plenty of sociology going on here. In fact, when I was talking to people who work on this over the summer, one of them told me, no offense, we don't need a philosopher, we need a sociologist. So there's a lot going on in that arena.
Katie.
I enjoyed the summary of where things are at with this problem. I have a couple papers on the Hubble tension, so I'm invested in this a little bit. But one of the, just as a comment, one of the things that we looked at in my research was not just looking at the one dimension of the Hubble constant, but also the matter density parameter, because all of these measurements land in different spaces on that two-dimensional space in ways that can be quite interesting to see where the agreement is actually not as good as it looks just from the one dimension of the Hubble constant in some of the sort of late time measurements. And so in that space, it looks more consistent with, more things look more consistent with the CFD stuff than in the one-dimensional space. So it's just an interesting kind of like different way of looking at that. My question is, what do you think is the fix?
Oh boy, might be above my pay grade. Yeah, I think it's hard to say because, you know, a lot of the problem with the new physics solutions is by tinkering around, you introduce new tensions. So like the sigma 8 tension is obviously the clearest one. So there's this minor tension there that is pre-existing right now between the sort of astrophysical measurements and Planck, but attempts to address the Hubble tension exacerbate sigma 8 tension. And so then we're kind of in the position we are now, but just with a different tension. And so that would kind of be a, you know, high price to pay. You have to accept something like early dark energy, and now we have a whole new tension that we have to introduce something else to deal with. You know, it doesn't seem so good. So again, don't get me wrong on this either. The pre-existing or the currently existing new physics proposals are not very satisfactory, and in part because of these additional tensions that are introduced. I mean, I think that of course this is a, it's a classic scenario where until some other model that explains everything the old one explains, and the Hubble tension, and definitely won't just be the Hubble tension, but other existing tensions that exist between other data sets comes along, there won't be any progress. The models that come out now that do these very ad hoc tweaks to just solve the Hubble tension to keep everything else the same, I mean, no, let's get real, nobody's going to accept that type of thing. It still might be useful for kind of exploring all the possible models to develop these, but I mean, I definitely don't think that's like a realistic way forward. I don't think people are ever going to accept that. So yeah, I guess creative theorizing, I don't know.
So would you say that you think the way forward is different cosmological theories, or is there something observationally that you think would be more helpful? Yeah,
the problem with the observations, again, it's not impossible, but the problem is the way people are going about it now is they're suggesting these possible systematics, for example, with Cepheids or something. And at this point, then you have to answer, okay, well, the Mega Maser Cosmology project doesn't use Cepheids, so how do you explain that one? And okay, so you suggest something strange with the masers. I mean, it's possible. And then you say, well, surface brightness fluctuations don't use that, you know. So yeah, it's I feel like I'm kind of as stumped as anyone because it seems like introducing new physics introduces new tensions, and suggesting these systematic errors in the distance ladder doesn't seem that helpful. And so continuing to multiply these observations, seeking out these systematic errors, it doesn't seem like it's getting anyone anywhere. It doesn't seem like it's doing anything. So there's this like stagnation, I don't know. I don't have a clear suggestion on the way forward.
Mike.
So I suppose this is somewhat in keeping with that line of conversation. I'm curious to what extent, I guess if you could pull up the final slide, that was just a really nice summary slide. Yeah. So number 2 here is, I wonder how tied the argument going on in 2 is to the more, was it Balsing? The stronger thesis that we can move away from thinking in terms of independence altogether, versus number 2 is just sort of an independent aspect of the argument here. In particular, like, if we are thinking moving away from independence, that somehow it's misguided to try to get independent access to the same thing, because in the background we think there's some new physics that might wed them together, so you'd never want to expect these independent samples to be saying the same thing. So I see how that goes through, but then if you're getting off the board with 2, in somewhat along the lines of what this last discussion was, where going for new physics and trying not to create new tensions, don't you want independence again? I mean,
Well, of course it'd be nice to have it, but that doesn't mean you do. It just seems like in part because of the fact that to get a Hubble constant out of a cosmic distance ladder, you're going to need information about expansion and things. It just seems like it's a feature of a lot of these measurements that they're not going to be fully independent. And likewise for some of the historical entanglements. So yeah, I mean, independence would be incredibly nice. But I think then my response would be suggest an independent measurement you could do that really is independent, and everyone will be happy to have it. Is it possible is the question. Yeah.
Right. I guess I was thinking, so you want, in theory, right, if you're hoping for the new physics angle, you'd really like these to be independent and about different parts of the physical system.
Yeah.
Because what you don't want is that there's some like degeneracy in the analysis where the way in which they're not independent is also actually covering for the fact that they're really just one thing and not two things. So the non-independence is causing there to be a discrepancy, but the discrepancy is fictional. It's due to the non-independence. They're in fact one thing. Whereas the new physics seems like anchored in, oh no, there are two things. There are two different phenomena in play here, and we need some sort of...
It could be. So here's the thing. So just because they're not independent, it doesn't mean that explains the Hubble tension in any way, right? Like the fact that you have to assume certain features of lambda CDM that you're also using to analyze the CMB, that you need to assume those things to get a cosmic distance ladder measurement. That's not then saying, oh, so the Hubble tension isn't a problem. If anything, you might think it's more of a problem, because if you're assuming these features of lambda CDM also in the distance ladder, then it seems like you have one model that's getting you these discrepant results, right? So that it's not the case that the fact that they're not independent, the fact that they're dependent is somehow a solution to the Hubble tension. So the new physics angle, the issue there then is if people are thinking about them as independent and they're developing sort of new physics that's meant to just tweak one side without realizing the dependencies, then that's kind of it's an artificial solution that when you actually do a full analysis is going to sort of break things here and there potentially. Not in every case, it depends on the specific dependencies and things like that. I don't know if that, was anything.
Yeah, I think so. The idea here is just there is an interesting interplay between if we're holding on to independence, how we hash out the cosmologist theorist challenge in line item 2, whereas if we're taking the stronger view and saying we should move away from thinking of independence, the argument for number 2 gets cashed out a bit differently.
Yeah, maybe we can talk about it more, because I'm not sure if I'm totally sure what you mean by it.
Thanks.
Yeah.
Any more questions? Well, if not, I would like to thank you again, Abigail, for the presentation, and thank Nick for the comments, and thank all of you for the questions. So let's thank Abigail.